Hello, everybody. So today we have another practice set with 10 questions. And these questions are mostly from Arrhenius equations. So let's start. First question, that's a good question. Arrhenius equation for two chemical reactions are K1 is equal to A1 e to the power minus E1 by RT and K2 is equal to A2 e to the power minus E2 by RT if, look at the conditions, if E1 is greater than E2, then at a given temperature, which of the following relation is true? Okay. So, first of all, two equations are given to us. Let's take the ratio because in all the equations, they have compared K1, K2, either multiplied them or divided them. So, let's take the ratio first of all. So, if we have K1 by K2, we will be having A1 e to the power minus E1 by RT divided by A2 e to the power minus E2 by RT. Okay? So this can be written as K1 by K2 is equal to A1 by A2. I'll take this exponential term to the top. So this will become e to the power plus E2 by RT. Correct? Plus E2 by RT into e to the power minus E1 by RT. So by RT is common. So I can write it as K1 by K2 is equal to A1 by A2 e to the power E2 minus E1 by RT. Okay, this is what we have got. Now, you can either take K1 by K2 or you can take K2 by K1. Anything is fine. So just to start with, I have taken K1 by K2. Any way you approach, you will get the same answer. Okay. Now, in the question, they have given that the value of E1 is greater than E2. Correct? The value of E1 is greater than E2. If so, then what will happen over here? In the power, that is K1 by K2 is equal to A1 by A2. As E1 is greater than E2, E2 minus E1 will be a negative number, correct? So this will be e to the power minus negative number by RT. Now, any negative number by RT is going to give you a negative number itself. So it's going to be e to the power something which is negative. E to the power something which is negative. Okay, now till here, you will get it very easily. Now, after this, you should do basic mathematics, without which you cannot do. Okay. Now, the thing that you should be knowing is the term e raised to a negative number will always be less than 1. Okay, when e is raised to negative 1, this is always going to be a number which is less than 1. For example, if I want to give you certain values, let's say I put e to the power minus 1. Example, this is just for your sake of understanding. If I put e to the power minus 1, the value that I'm getting is 0.36. Okay. Let's say that I put e to the power minus 0.1. Again, this is negative. Some number which is negative. So what I'm getting is 0.904. Okay. Likewise, if I put a very huge number, let's say, if I put, let's say I'm putting e to the power minus 10. Then what I'm getting is 0.000045. So as you can see, e to the power any negative number, whatever you put, whether it is small or whether it is large, it is going to be less than 1. Correct? So what you're getting is K1 by K2 is equal to A1 by A2 into a number which is less than 1. Now you can, for the sake of understanding, you can put any value. You can put any value. For example, let's say that the value that you have got, you can put any value which is less than 1. Let's say I have put 0.5. 0.5 is 1 by 2. This is just for your sake of understanding. This value is arbitrary. You can take 1 by 2, you can take 1 by 5, you can take 1 by 10, you can take 1 by 100, whatever you want, you can take any number which is less than 1. This is just for the sake of understanding. Okay, so I have got this, I'll write it over here. Suppose e to the power negative number is equal to 1 by 2. Somehow we got 1 by 2, let's say. Okay, then see what is the relation. If I take 2 to the side, k1 by k2 into 2 is a1 by a2. From this, what can you conclude? If I have to get a1 by a2, I have to multiply the value of k1 by k2 with 2. Understand? For example, again, let's take example so that you can understand it better. Let's say that k1 by k2 is equal to 5. Let's say k1 by k2 is equal to 5. Then what will be the value of a1 by a2? a1 by a2 will be 5 into 2, which is 10. Correct? So, with this relation, you're getting a1 by a2 is larger than k1 by k2. a1 by a2 is larger than k1 by k2. Let's see if we have a relation of that sort. Yes, option A. a1 by a2 is larger than k1 by k2. So the correct option is option A. Correct option is option A. Easy. Okay, it's easy until here. Then you should have your basic mathematics knowledge. That's all. Okay. Next question. As in gate, the dependence of rate constant K on temperature T, which is given in Kelvin, of a reaction is given by ln K is equal to minus 5000 K by T plus 10. The activation energy in kilojoules per mole. Please be careful. It's not joules per mole. It is kilojoules per mole. And they have asked us to round it to 2 decimal places. Okay, now you already know that Arrhenius equation is K is equal to A e to the power minus EA by RT. Now if we take ln on both sides, what we'll get? Ln K is equal to ln A minus EA by RT. Correct? Now if you compare with what is given in the question, what is given in the question? In the question it is given ln K is equal to 10 minus 5000 by RT. Correct? This is given in the question. So if I compare the general equation of Arrhenius equation with what is given in the question, we can get that EA is equal to 5000. Correct? This minus is common. RT is also common. So if you equate these two, what I'm getting is EA is equal to, there is a K, right? There is a K. Okay. You need that for units conversion. Okay, not conversion, cancellation. Okay, so what we're getting is, if I want to write it like this, minus EA by RT is equal to minus 5000 K by RT. Correct? No. In the question, this TR is not given. Okay, this is wrong. Yeah, it's like this. This is something that we get. Now on the LHS and on the RHS, minus is common. T is also common. So from this, what I can write is minus gets cancelled. What we have is EA by R is equal to 5000 K. 5000 K. Now it is easy. You need to find the activation energy, which is simply the value 5000 K into R. What is the value of R? It is actually 8.314 joules per Kelvin per moles. Now, there is a Kelvin over here. There is per Kelvin over here. That gets cancelled. And whatever answer that you get over here will be in joules per mole. Be careful. Okay. So, in order to get your final answer in kilojoules, you need to multiply it with 10 to the power minus 3 so that you get it in kilojoules. Very important. How do you convert joules to kilojoules? You will divide it by 1000. Correct? Dividing by 1000 is same as multiplying with 10 to the power minus 3. Right? Now you can use your calculators. 5,000 into 8.314 into 10 to the power minus 3 kilojoules per mole. The final answer that I'm getting is 41.57 kilojoules per mole. You need to round it off to 2 decimal places. That's why I have taken only 2 decimal places. In the answer key, the range was given as 41.50 to 41.60. So if you give any answer with 2 decimal places within this range, you will get the marks. Okay? So it's easy. Be careful of the unit conversion over here. Sorry, not conversion, cancellation. Okay? Unit cancellation. All right. Next question. I have already done the answer. This is in order to save the time while solving the problems. You people should not directly write the answers. You have to use your scientific calculators and write the answers. Okay? Otherwise, for the exam, you'll find it very difficult. Next one. The activation energy of a reaction reduces by 12 kilocalories per mole. Look at the units. It's 12 kilocalories in the presence of an enzyme at 300 Kelvin. Assuming pseudo first order kinetics, calculate the factor by which the reactant rate is increased. Okay. Okay, let me read the question once again. The activation energy of a reaction reduces by, so some reduction is happening in the presence of an enzyme. So you have a system without enzyme and you have a system with enzyme. The difference in the activation energies are given. You have to find the rate by which the rate constant is increasing. Okay, that's all. So let's write down the equations first of all. So let's say that the rate constant with enzyme. Okay, WE stands for with enzyme. The rate constant with enzyme is equal to, what is our equation? Pre-exponential factor, activation energy e to the power minus EA with enzyme by RT. Okay. And you have a system without enzyme. So I have written O for without enzyme. And that is A e to the power minus EA without enzyme by RT is what you have. Correct. This is what you have. Now let's say I divide 1 by 2. If I divide 1 by 2, what do I get? The rate constant with enzyme divided by the rate constant without enzyme. That is what we have to find in the question also. Calculate the factor by which reaction rate is increased. That is, you have to find with enzyme, whatever the rate constant is, that is equal to how many times the rate constant without enzyme. The rate constant with enzyme is equal to how many times the rate constant without enzyme is what you have to find. Okay. So we'll take the ratio. If you take the ratio, this pre-exponential factors, nothing is told. So you will assume it to be the same. And this is equal to, if you divide this term which comes in the denominator, okay, I'll write minus EA with enzyme by RT divided by e to the power minus EA without enzyme by RT. Now, if this comes to the top, this will become plus, correct? E to the power activation energy without enzyme minus activation energy with enzyme divided by RT it is. This is what you get. Now, see, in the question, they have given that when you add the enzyme, the activation energy of the reaction reduces. Got it? So this value of the activation energy without enzyme minus the activation energy with the enzyme is already given. They have said that when you add, so you already know, right? Let's say this is without the enzyme. And with enzyme, you're active. This is with enzyme. So with enzyme, your activation energy reduces. So this difference is what is given to us. Correct? This difference is what is given to us. So this comes out to be the rate constant with enzyme divided by the rate constant without the enzyme is equal to e to the power how much? 12 kilocalories. So that means 12,000 calories per mole divided by the value of R that you take. Very, very, very important. Why? Because it is in calories. The value of R that you take should also be in calories. Actually, the value of R is 1.98 calories per Kelvin per mole. But as the units or as the values in the options are very far apart, you can approximate it as 2 calories as well. No problem. Okay. So this is coming out to be 2 calories per Kelvin per mole. What is the temperature? Temperature of the system is given as 300 Kelvin. So you will put 300 Kelvin and per Kelvin, Kelvin gets cancelled. Calories on the top, calories at the bottom. Per mole at the top, per mole at the bottom. Okay, so you have 12,000 divided by 600. So rate constant with enzyme divided by rate constant without enzyme is equal to e to the power 12,000 divided by 600, which is going to be equal to e to the power plus 20. Okay. So while doing this, the answer that I'm getting is 4.8 into 10 to the power 8. That means my rate constant with enzyme is 4.8 into 10 to the power 8 times the rate constant without my enzyme. Okay, this is what I'm getting. So if you check the options, this is approximately same as D. They have rounded off. So the correct answer is option D. Correct answer is option D. Question asked in 2018. Next question. The rate constant of a first order reaction is given as x giving y is something at 300 Kelvin. Okay, I made a mistake while solving this problem, so pay attention. The rate constant is given at 300 Kelvin. Given the activation energy of the reaction is 28 kilojoules per mole, and assuming Arrhenius behavior for the temperature dependence, the total time which is required to obtain 90% of Y at 350 Kelvin is. This is where I made the mistake. So see, they have given the rate constant at 300 and they are asking the 90% product formation at some different temperature. Okay, so don't make a mistake over here. What I did is, this is rate constant K at some temperature. They have asked T. I directly used the first order kinetics equation and I got some answer and I found that it is wrong. Okay, so be careful. Why? Because they have asked the time required to obtain some amount of Y at a different temperature. So you need Arrhenius equation here. Okay, so yeah, let's try. All right, so we need to find the time which is required for obtaining 90% of Y at a different temperature, for which you don't know the rate constant. Very important. Here, the rate constant at 300 is what is given. We need to find the rate constant of the reaction 350. Why? Why? Because integrated rate equation for the first order reaction is integrated rate equation of first order reaction, as you already know, that T is equal to, or KT is equal to ln of initial concentration divided by the final concentration. Now the reaction that is given to you is X giving Y. And they are asking that you need 90% of the Y to be formed. What does that mean? Let's say that this is 100 initially and Y you don't know. And not you don't know, no Y is formed. Okay, they are asking the time at which the amount of Y formed is 90 So how much of X will be remaining? Of course, 10. How 10? Because 100 minus 90, out of which this 90 is what is appearing as Y, and this 100 minus 90 is 10. So the amount of the reactant left is 10 if the initial concentration is 100. Correct. Okay, I hope this is clear. So if then, what we can do is the time at which the final concentration is of the reactant is 10 at a temperature of 350 is what they have asked. So this is equal to 1 by rate constant at 350 into ln of initial concentration 100, concentration is 10, and this comes out to be ln 10, but you need to know K350, for which you need Arrhenius equation. Okay, so that's the tricky part of the question. Otherwise, it's easy. Okay, so let's start. Let's start. You have two temperatures. So when you have two temperatures, the relations are K350 by K300 is equal to EA by R into 1 by T1 minus T2 it is. So 1 by 300 minus 1 by 350. Correct? The EA for the process is already given. It is 28 kilojoules. I'll put it in the next step. 350 divided by the rate constant at 300 is also given. It's 1.6 into 10 to the power minus 3 per second. Activation energy is given as 28,000 joules per mole divided by R is given. No, R is not given. You have to take. So if it is in joules, you can take it as 8.314 joules per Kelvin per mole into 350 minus 300 Kelvin is 50 Kelvin divided by 300 into 350. So this is also Kelvin, this is also Kelvin. Okay. This is also Kelvin, this is also in Kelvin. Always write the units to be on the safe side, please. So if we look at the units, Kelvin, Kelvin gets cancelled. Here there is Kelvin, here there is per Kelvin. Joules, joules get cancelled. Per mole gets cancelled. So finally what you have is the rate constant at 350 is equal to 28,000 into 1.6 into 10 to the power minus 3 per second divided by 8.314 into 50 by 300 into 350. This is what you have to solve. Use your scientific calculators. Pause the video if you have not tried this. Please do not copy paste the answer that I'm giving to you. Okay, so what I'm getting is 7.95 into 10 to the power minus 3 per second. Now you have got the rate constant. You plug it over here. That's all. So the time required is 1 by 7.95 into 10 to the power minus 3 per second. Ln of 100 by 10 is ln 10. Okay. So the answer that I'm getting is 289.64 seconds. And in the question, they have asked us to approximate it to the nearest integer. That means without any decimal points. So if I round this off, my final answer that I'm getting is 290. 290 seconds. And in the answer key, they had, in the key, they gave a very wide range of 280 to 300. So any integer that you write between 280 to 300 was considered to be right. Okay. A similar question in the next question as well. Sorry, a similar type of question. So for a reaction raising the temperature from 200 Kelvin, which is T1, to 300 Kelvin, which is T2, results in an increase in the rate constant by 2. Okay. So the activation energy in kilojoules per mole is closest to. Very easy, correct? So what is the equation? We know that ln of K2 by K1. Just a second. I didn't write ln over here. I had calculated it, but I didn't write it over here. There is ln, okay? There is ln over here. Sorry, I missed it out. There is ln. I have taken that. Okay. So you cannot take this directly over here. This is ln of K350 by K300. You will get an answer. Okay. You will get an answer from this. And then you have to take the anti-ln and then multiply. Okay. So finally, whatever you get over here is rate constant at 350. Okay. I hope you understood. Let's say that you got this as x. Okay. That means ln of K350 by K300, you got some answer as x. Then K350 by K300 is actually e to the power x. And that e to the power x, you will have to multiply it with K300 in order to get K350. Okay. Yeah. So be careful with that. Okay. I'm sorry. Yeah. So over here, ln of K2 by K1 is equal to EA by R into 1 by T1 minus 1 by T2. Okay. So they have already said that when you increase the temperature, the rate constant increases by a factor of 2. So in the question, it's already given that K2 by K1 is equal to 2. Correct. So ln 2 is equal to EA is what you have to find divided by, you have to find in kilojoules per mole. So you better write your value of R in kilojoules as well. So 8.314 into 10 to the power minus 3 kilojoules per Kelvin per mole into T2 minus T1. So it is 300 minus 200, 100 Kelvin divided by 300 Kelvin into 200 Kelvin it is. Correct? So your, if I have to cancel the units, K gets cancelled over here. Kelvin per Kelvin gets cancelled over here. So your activation energy is equal to ln 2 into 8.314 into 3 into 2 is 6 followed by 4 zeros divided by 100. This is what you get. I'm getting an answer approximately equal to 3.4 kilojoules per mole. And the closest answer among the option is option B. Option B. Okay. Next question, again from the same equation. The rate constants for the decomposition of a molecule in the presence of O2 are, so let's say this is temperature T1. It is 0 degrees Celsius, which is given. You can convert it into Kelvin. You should convert it into Kelvin. So you need to add 273 to this. So at 273, your rate constant is K1. And at 25 degrees Celsius, which is T2, which comes out to be 298 Kelvin, your rate constant is K2. The value of R is given. Don't expect this for the question. Activation energy in kilojoules per mole is very easy. You have to round it to 1 decimal place. Now you know which equation is to be taken. Ln of K2 by K1 is equal to EA by R. You have to put in kilojoules because the answer that they are asking is in kilojoules. 1 by T1 minus 1 by T2. Correct? All the values are given. So ln of, what is the rate constant? 2.64 into 10 to the power minus 4 divided by 0.237 into 10 to the power, there is a minus here, into 10 to the power minus 4 equal to EA is what you have to find, divided by 8.314 kilojoules per Kelvin per mole into 298 Kelvin minus 273 Kelvin divided by 298 Kelvin into 273 Kelvin. You need to rearrange. We have already done in a similar problem. I'm not doing it again. Finally, the activation energy that you get, and after rounding off to one decimal place, I'm getting 65.2 kilojoules per mole. 65.2 kilojoules per mole. In the answer key, it was a value between 65.0 to 66.0. Okay. Next question. Question number 7. The correct graphical representation describing the temperature dependence on the rate constant is. So by now you might have understood how important is this topic of Arrhenius equation and the graphical questions. We have already done many of them. So the question what they are asking is K versus 1 by T. K versus 1 by T. So let's try. So we already know that K is equal to A e to the power minus EA by RT. Correct. So if I have to write it, I'll write it as A e to the power minus EA minus EA by R into 1 by T. It's the same thing. I'm just writing it for your sake of understanding. So K is equal to A e to the power minus EA by R, which is some constant, into, this is our X, variable along X. So if I have to take it to the denominator, what I can write is K is equal to A divided by e to the power, this is some constant, I'm not bothered about the constant, minus some constant into X. So this minus when comes to the denominator, it becomes plus. I'm sorry. So this minus when it comes to the denominator, it becomes plus. Now listen carefully. If your X, which is the power of the exponential, increases, if your X increases, your overall value of e to the power ax also increases, correct? E to the power 2 is less than e to the power 3 is less than e to the power 4. So as your power increases, your whole value of exponential also increases. Correct. So as x increases, the overall exponential term increases. And if the overall exponential term which lies in the denominator increases, now see, this is inversely proportional. This is in the denominator. K is over here, so this as a whole will decrease. So, if 1 by T increases, your K decreases. So, it's not option B, it's not option D. It's either A or C. As exponential is involved, it's not going to be linear. So, the correct option is option A. Okay, next question. Two reactions have same pre-exponential factor, but the activation energy of the first reaction is lower than the second reaction by 5 kilocalories per mole. Be careful, 5 kilocalories per mole. The ratio of the rate constants of the first and the second reactions are. So the question is the ratio of K1 by K2. Okay, now you know K1 is equal to A e to the power minus E1 by RT. K2 is equal to A e to the power minus E2 by RT. And what they have asked is the ratio of K1 by K2. Pre-exponential factors are the same, they have already said, so that gets cancelled. So this comes out to be e to the power. Upon taking the ratio, this comes to the top and this becomes E2 minus E1 by RT. Okay. Now it's already given that your activation energy of the first reaction, E1, is lower than the second. So this value is small. E1 is smaller than E2 by how much? 5 kilocalories per mole is what they have given. So I can write it as K1 by K2 is equal to E2 minus E1 is 5 kilocalories. So this is to the power 5000, I can write calories per Kelvin per mole divided by the value of R that you take. is very important. You know that the value of R is 2 calories per Kelvin per mole. Sorry, in the question, the activation energy is just calories per mole. Kelvin is not. Okay. So this is the value of R that you should take, and the temperature condition is 298 Kelvin. Okay. You can cancel calories, per Kelvin, per mole, mole, and finally you will get the ratio K1 by K2 e to the power 5000 by 2 into 298. Once you do this, you will get an answer which is approximately equal to 4650. Approximately. That is option A. Option A, question which was asked in December 2023. Okay. Next question. The correct statement about the pre-exponential factor in Arrhenius equation is option A, it is dimensionless. Is that true? C, already we know that K is equal to A e to the power minus EA by RT, out of which this term, this exponential term is dimensionless. But the units of A will be same as the unit of K. Correct? Units of K will be same as that of A. So let's say that it is a first order reaction. Then the unit of K will be moles per liter per second. And that will be the unit of A as well. Sorry, that is for a zero order reaction. If it is a first order reaction, it is going to be per second. If it is going to be a second order reaction, it is liter per moles per second. That you know. You already know how to derive the rate constants ka unit. So in the first option, it is saying that it is dimensionless. No, it is not dimensionless. It has dimensions of the rate constant. Okay, so this is wrong. Second one, it has a unit of per second regardless of the order. That is true. Correct? Even if it is zero order, first order, second order, in all the orders, irrespective of the orders, you have this dimension of per second. That is true. In C, it does not necessarily have per second. It has. It has per second, so C is wrong. D, it has concentration in its dimension regardless of the order. Okay, that's not true because in the first order, you don't have any dimensions of concentration. So the correct answer is option B. See, this question was asked in June 2024, a statement type question. Okay. Last question. Again asked in June 2024, the same paper. The reaction A giving P consists of the following steps. 3 steps are given, out of which the third step is slow. The activation energy of the overall reaction is very easy. What is given? A is becoming I is reversibly becoming A, and this I is also becoming P, out of which this is the slowest step. Correct? So if I write this as K1, this is K2, this is K3, respective activation energies are also given. So rate is always the slowest step and slowest step is mentioned. So rate is equal to K3 into concentration of I. Now, concentration of I should be eliminated because that is an intermediate. Now it is already given that this is under fast equilibrium, so you can use approximation method to eliminate. So with approximation method, we know that K1 by K2, which is equilibrium constant, is equal to concentration of I divided by concentration of A, from which concentration of I is equal to K1 concentration of A by K2. I'll put it over here. So my rate is K1, K3 concentration of A divided by K2. Very easy. So what is your overall rate constant of the process? K1, K3 by K2. So if this is your rate constant, how do you write the expression for the overall activation energy? So wherever there is into, that will appear as plus in the overall reaction. Wherever there is division, that will appear as minus. Very important. So K1 into K3 will appear as EA1 plus EA3, and K2 is divided by K2, that will appear as minus EA2. Very easy question which was asked recently in 2024. Yeah. So it is EA1 plus EA3 minus EA2. Option B is the correct answer. Okay, so with that, we have completed most of the questions from part 2 of chemical kinetics. And in the next assignment, you'll get questions from enzyme catalysis. Okay, so that's all. Bye-bye.